Alright, pre-calculus class, we're going to look over the 2.3 set of notes. The big thing we're going to do here today is talk about polynomial functions. Okay, that is the big goal of 2.3, is the introduction to polynomial functions. We're also going to look at their behavior, their characteristics, finding the zeros and the multiplicities of zeros, just a lot of stuff about polynomials. Alright, if we have a function that looks at this form, and looks kind of a spooky form, but the big thing is n is a non-negative integer, so that's just whole numbers. So 0, 1, 2, ... just on and on and on. Then that's what we refer to as a polynomial function of degree n. The number a sub n is the coefficient of the variable to the highest power, and that's called what we refer to as the leading coefficient. So some examples, just so you understand that f of x equals x to the n is the highest power of all these. You can see n minus 1, n minus 2, on and on, until we get down to 2, 1, 0, 0 being x to the 0 would be like a constant. Anything with 0 is 1, so any number times 1 is 1. And then a sub n, x to the n. A sub n is just a number that's in front of x to the n. So for instance, like if I had 5x cubed plus 3x squared minus 7x plus 2, right? A sub n would be 5, right? N would be 3. N is the highest power. A sub n would be the number in front of x to the highest power. A sub 2 would be 3. It's the number in front of x squared. A sub 0 is the constant. It's just the number that doesn't have an x multiplied by it. So these are just basic polynomials, things that you've seen before. It's just maybe a new way to see them described, or a very mathematical way, at very least, to see them described. But they're not difficult to work with. All right, polynomials that are degree 2 or higher have graphs that are smooth and continuous. And that's the same thing that's going to be down here. By smooth, we mean the graphs contain only rounded curves. They just, they bend very slowly like that. They don't have any sharp, jagged points like that. So this will not be seen on the graph of a polynomial. And continuous, by continuous, we mean the graphs have no breaks, no asymptotes, no gaps. So we're going along, you're not going to find a hole in the graph, followed by like a gap, followed by something known as a vertical asymptote that we'll get into later. You're not going to see anything like that with polynomials. They're all going to be smooth, connected, in a way that you can think about it, that it mentions right here. You can, once you get into the graphing area, there'll be an x and a y. But once you enter, wherever you may enter, you can draw everything that you need to in there without ever lifting your pen or your pencil to graph it. End behavior is a very, very important concept in this section. End behavior sounds like what it is. It's the left and right end behavior. So there's the left end, there's the right end. So what does the graph do on the ends? And what we find out with polynomials is they either always rise as we make our way to the end, or they always fall as we make our way to the end. Now in between they'll bend and do all these different things. But on the right and left end, they're always going to either rise forever to infinity or fall forever. So this is what we refer to as the leading coefficient test. I'm going to blow it up a little bit more. It's not much more, but just a little more so you can see it. And what it basically says is when we have these functions, leading coefficient, remember, is that guy right there. So the power itself, n is odd, n is even. The power itself splits us into these categories. If it's an odd leading power, highest power, then we're either going to rise on one end and fall on the other, like rise to the left, fall to the right, or we're going to rise to the left. Fall to the left, rise to the right, or rise to the left, fall to the right. But we're going to do opposite things on each end. Rise, fall, or fall, rise. But when it's even, we have like a highest power of 4 or 2 or 6 or something like that. Then whatever we do on the right, we also do on the left. And vice versa. Whatever we do on the left, we also do on the right. So we're going to rise and rise, or fall and fall. And that's what the leading coefficient test says. All right, it says use the leading coefficient test to determine the end behavior of a graph that's x to the 4th minus 4x squared. All right, so number one, we don't need this. Right? This is the leading term. It's the highest power term. And it's got an even power, and the leading coefficient, which is, again, I could just call it a sub n, is equal to positive 1. Right? 1x to the fourth. So what did the last side say? Well, it's even, so that means we're over here with one of these two options. And the leading coefficient is positive. So it's going to rise to the right, it's going to rise to the left. So this graph will rise right, rise left. Now, underneath this picture, I've got just a rectangle that I'm going to remove. This rectangle has the graph of it. So if you ever are stumped on these, just graph it and see what happens on the right and left side. So there's the graph of this function, and you can see, you can confirm there we are rising to the left, we're rising to the right. So that's what we would write. When you are asked what is the leading, what is the end behavior of the graph, then you're going to write rises left, rises right, falls left, falls. You're going to write one of these combinations. There's only 4 possibilities for end behavior, so you're going to write one of those, and it's all determined by the even or oddness of the highest power on x, and then the sign in front of x to that highest power. Those two combinations will let you know what is going to happen on the left and right end of the graph. All right, let's look at the zeros of a polynomial function. So if f is a polynomial function, and we call the values of x that make the output 0 the zeros of f. And that's not unique for polynomial functions. That's basically any function. We call them the zeros of the function. But the x values are just the roots or the solutions of the polynomial equation, that function, that polynomial set equal to 0. And each real root, this is important that this only happens for the real roots. We'll talk about complex roots later. But each real root of the polynomial equation appears as an x-intercept in the graph of that polynomial function. Okay, so if I'm looking at a graph, function crosses right there, and it comes down, and it goes up, and it comes down over here, something like that, then that is a real, and these are 2 of the zeros of the polynomial equation. So they're the real roots, the real zeros, those terms are used interchangeably. All right, find all the zeros of this function. So the way that we're told to do this, and if you click on View an Example, it would tell you to set the function equal to 0. Right, that's what it says right there. Set the function equal to 0. And then come up with some type of technique to find out what makes that 0. So when we have 4 terms, and I say that 1, 2, 3, 4, the 4 terms are the things that are the number of polynomial things that are being added and subtracted. The x's to the different powers that are being added or subtracted are the terms. If you have 4 terms, then the typical way you do it is by grouping, which means you group the x cubed, x squared terms together, you group the x and the constant terms together, and then you pull the GCF out of each group. So the GCF in this first group is equal to x squared. The GCF in this second group is equal to negative. So if I pull out an x squared out of that first group, I'm going to end up with an x plus 2. If I pull out the negative 4 in this second group, I'll also end up with x plus 2. And that's how we know if this factoring technique works, is we end up with the same thing after I've pulled out the GCF. All right, if that works, then you're going to be able to factor this by grouping. All right, now it's the things that are in the parentheses multiplied by those GCFs that we pulled out parentheses. All right, and technically all I'm doing there is I'm factoring out that common x plus 2. All right, now I've got multiplication set equal to 0, so that means that I can set each piece equal to 0. So x plus 2 could be 0, which would mean x is equal to negative 2, or x squared minus 4 could be 0, which means x could be negative 2, but it could also be positive. I square a negative, I get positive 4. If I square positive 2, I get positive. Either way would give me 0 if I subtract 4. All right, you can see that x minus 2 shows up twice in these solutions. All right, we're going to give that a name on the next slide, but this one only shows up once. Okay, so we see this 2 times, and we see this 1 time. Right, so that's important for what we're going to see on this next slide. The reason why it's so important is x equals 2, the positive 2 occurred once, and you can see that I crossed the graph. The graph crosses at that 0. But negative 2 occurs 2 times, and you can see the graph turns and touches there. It doesn't cross. And that's a very important concept that we refer to as multiplicity. So when we cross, or where we cross, is determined by these factors. Right? X plus 2, that's a factor. Technically, this x minus 4 could be written as x squared minus 4 is x plus 2, x minus 2. That's called a difference of squares. And so we end up with this x plus 2 from this own factor right here. And then this x plus 2, x minus 2, that also has an x plus 2 in it. So if you think about it, we actually have x plus 2 occurring twice in this factored form. It'd be like picking up from here, coming to there, setting it equal to 0. So this x plus 2 is a factor 2 times, and that's what this is saying. If x, technically minus r, would be minus negative 2, occurs k times. So it occurred 2 times, but not k plus 1, not 3 times. Then we call minus r, negative 2, a 0th multiplicity k. It occurred 2 times. Alright, so that's even multiplicity, and you can see the graph touches the x-axis and turns around. That's exactly what we were seeing right there. It touches and turns around. But when it was odd, right, that x minus 2 occurred only 1 time in this factored form. Then we cross the axis there. Alright, so odd multiplicity, we cross. Even multiplicity, we touch and turn. Okay, that's going to be very important that you understand for these sections when we're doing these problems. So here is a factored, it's already in a factored form, right? And we can see that 2, that's even. So that means we're going to touch and turn. But 3 is odd, so we are going to cross. Right? And if we look at the graph, we can confirm that that does happen. There's our 0 that, what makes this 0? This piece right here, x equals negative 2 does. Or sorry, negative a half does. There's negative a half, and you can see it's even, touch and turn. Right? What makes this equal to 0? 5 does, positive 5 does. Because it's odd, we cross. Now it does flatten out. It doesn't just cross directly like there's 5. It doesn't just go straight through like it would if this had been a 1. It always will be the case that the higher the odd number, the more it flattens out at the place where it crosses. The same thing goes with the even numbers. The higher the even number, the more it flattens out. Like, for instance, there is x squared if you just graph y equals x squared. But if you graph y equals x to the 4th or the 6th or something like that, you'll see it turns and touches, but it also flattens out a lot before it turns and touches. So the higher the power that's even, the basically longer it takes to make that complete U-turn. Same way with crossing for odd numbers. The higher the odd number, the more it flattens out as it crosses. Right, intermediate, kind of that means like in the middle. So we have a value in the middle. So if we have opposite signs for the output, remember these are y's. So if the y's are opposite signs, so here's an x-axis. So there's A, there's B. So opposite signs, so like here I'm negative and here I'm positive. If we have a continuous function, again, polynomials are continuous, then if I make my way from the output at A to the output at B, I'm going to have to, there's no way, because it's a function that's continuous, there's no way I can avoid crossing the x-axis. So we will have to find a real root or a 0 in between A and B on the axis. So this is just a function or an example that shows you that. If I plug negative 3 into this function, I get out negative 42. If I plug in negative 2, however, I get out positive 5. So this is a polynomial. X is the whole number of powers. Negative number for the output, positive number for the output. That means I do cross somewhere in between there. Here's a Desmos graph just to confirm it. All right, you can see there that there's the negative output at negative 3. There is the positive output at negative 2. And you can see that I do cross it, negative 2.171-ish. That is between negative 2 and negative 3 where we cross. All right, useful information here too, the turning points in a polynomial function. So if a polynomial function is degree n, then the most it can turn is n minus 1 times. So a degree 5 polynomial could turn 4 times, but it couldn't turn 5 or 6 or 8 times. Now it does say here that it has at most. So a degree, like for instance, a degree 3 polynomial, x cubed, if you've ever graphed that. It goes up, it bends, and it crosses, something like that. It looks something similar to that. And this is, the bin 1, this is the bin 2. It's not completely changing direction. Like that's 1, that's 2. These are both degree 3 polynomials. But they can be very subtle bends, or they can be complete like U-turns. It just depends on the polynomial. Okay, so when you're looking at them, sometimes these bends are so subtle that you could have a degree 5 polynomial and it bends 1 time, 2 times, and then maybe there's this little tiny subtle bend that does like that. So that's 1, 2, and then 3, 4 that are just so subtle that you can hardly see it, and the graph ends up looking like that. And from an untrained eye, that would look like just 2 bends. All right, but some of them are very slow, not complete U-turns. So I like to call these types of bends, like 3 and 4, like the lane changers. I'm on a road, I'm in the passing lane, and I get past the car that I'm trying to pass, and now I'm just going to change lanes. One turn is going to start me into the right lane, and then the other turn is to correct it so I don't just bash into the guardrail. So it's, we don't have to completely do a U-turn, for it to be counted as a bend. All right, then if we ever need to graph a polynomial, just sketch one by hand. These are the steps to do. You can kind of look through and see. But what it's talking about is start off with the end behavior, determine that I rise to the left, fall to the right, fall to the left, rise to the right, based on the function that I see. Right, find the x-intercepts by either factoring the polynomial. This one's already factored, but factor it if we can. Negative 2 is a 0, 3 is a 0. So I know it's going to do something like that. Negative, then use the multiplicities. It talks about using the multiplicities to get the behavior at the zeros right. So it's going to turn and touch at negative 2. So it's going to do something like that. It's going to cross at 3. So it's going to do something like that. And then the y-intercept in addition to the x-intercepts. So x-intercepts is what we're doing here in 2. Y-intercept on 3. So the y-intercept would be f of 0. Remember we said that notation, f of 0 is the y-intercept. So this would be 2, 0 plus 2 squared, and 0 minus 3. So 2 squared is 4, so this would be 2 times 4 times negative 3. So that is 8 times negative 3, that's negative 24. So you can see this is way out of the window that I'm having right now, this y-intercept. It goes very steep and comes back up very steep. It goes out of the window that we're given. Alright, so you can see it's out of the window there, so you may have to scale it to get there's the y-intercept. And we're still out of the window. You can plug these numbers into the function to kind of get your window right. But Desmos makes this so easy. So I'm just typing in f of x into this expression, and I can see what we were talking about before. There's that turning and touching, there's that crossing behavior because of the even and odd powers. But you can see that that place where it turns in between negative 2 and 3, it's out of the screen. So is the y-intercept. So watch, all you have to do with Desmos, you can move your cursor to the y-axis. That's what's out of the screen. Hold down shift and you can see the y-axis turns blue. And then I can just drag down until that point comes into the picture. Right? And let's say that, I see that 0, negative 20, negative 40, so you can see it's counting by 20s. It just does a kind of a prediction of what might be a good scaling for you. But if you wanted it to be 10s, you could come over to this graph settings, the wrench tool, and then just change the y-axis step size to 10. And now it fills in those gaps for you. And if you're thinking, oh, I don't need any of this stuff between like negative 5 and 10 because there's nothing there, there's nothing there on the right side, you can do the same thing we did to the y-axis to the x-axis. Just point your cursor at the x-axis, hold down shift and drag. Right? If it goes out of the picture in a different direction, you can move this around. It's very easy to find the correct windows for these polynomial graphs with Desmos. So you will see graph questions, in behavior questions, all kinds of stuff that can easily be answered with a graph. So just use Desmos. Desmos is going to help out a ton when you're doing these graphing polynomial questions and matching the graphs.